Example 4.2. A heat engine uses 0.02 moles of a diatomic gas as its working substance. A. Identify the heatings Q hot and Q cold, and which states are T hot and T cold. What is the Carnot and thermal efficiency of this engine? Draw a scaled energy transfer diagram for the situation that includes values of QH, QC, and W. So for starters here, we need to identify what is Q hot, T hot, Q cold, and T cold. So the best way to do this is I'm going to draw an energy bar diagram. And so that implies here is that if I have positive heats, that means that that's coming from the hot reservoir. If I have negative heats, that means that's the heat being ejected out of this cycle here. So let's go look at the cycle here now. So if I look at my cycle, I'm going to put a diagram right over here, PV diagram, because I'm going to use it here. Let's look at that. Assume by looking at this, the lowest energy state has to be 1. If you just look at PV, that's going to tell you that. So then here I go. This is my lowest energy state, in this case, E1. So now what happens? I do an adiabatic compression. If I do an adiabatic compression here, then that means that this work is going to go up. Let's say that this is the amount of work that I do when I do this adiabatic compression. And I know that my heat along an adiabatic compression is 0. So that means then my internal energy has now changed to this height right here. So this here is my internal energy at 2. So when I go along 2 to 3, I have isobaric heating. And isobaric heating, when I start to look at this thing, note that the area from 1 to 2 has to be smaller than the area from 2 to 3. So what I'm going to do here is that I'm going to make this area 3 squares instead of 2 squares. So here I go. So this here is my area for the work going from 2 to 3. Now note, it has to be negative because it's a expansion, but I know that the highest internal energy has to be at 3. So then if I look at this, the internal energy has to do what? I have to add this amount of heat just to knock off the work. And then let's say that this heat then takes this even higher. So now what you're seeing here is that I now have my heating from 2 to 3. And that should give me an internal energy that looks like this. So I'm going to increase it by 2 squares. So then I have to have it like this. So this is my internal energy at 3. But now, here's what we see. I have isobaric cooling. So heat has to be ejected out. So when I look at my bars, I have to get to this energy state, E1. So what I'm seeing here is that I got 1, 2, 3, 4. So that means then I have to bring down this guy by 4 squares. And this guy's going to be the heating from 3 to 1. So now it looks like this. And of course, I know that right here, my work from 3 to 1 is 0 since it's isobaric. So immediately what we can see here is that we have what? I know what my heatings are. Clearly, in this situation, I could say that from this diagram, I can immediately see that I only have one positive heat. So therefore, my Q hot is the heat that comes in from 2 to 3. This guy goes in. So I know my Q hot is heat 2, 3, and I know my Q cold has to be the only heat that's ejected here. And the only heat that's ejected is going from 3 to 1. And that guy goes out. So I immediately can identify what is the heats from the cold and hot reservoir. So now I could just see which state has the highest internal energy. The highest internal energy has to be, so I now know that the highest internal energy is proportional to the temperature. So that tells me that the highest internal energy has to be at temperature here. So let me call that T hot, which is T3. And the lowest internal energy has to be at 1. So then my T cold is at T1. So now I know everything about how the reservoir is working and what locations are the temperature. So now that I've done that, I'm going to go calculate the Carnot efficiency here. So now the first thing I'm going to do, I'm going to look at the Carnot efficiency. Eta Carnot, which I know is the maximum efficiency here. So I know that I have a diatomic gas. Is for the Carnot, it's going to be 1 minus the temperature of the cold divided by the hot temperature, which in this case is going to be 1 minus T1, T3. Now, note, we don't have any temperatures. So I'm going to convert everything with the ideal gas law. So then if I replace this with the ideal gas law, this is going to be P1, V1, and R, P3, V3, and R. Clearly, we see that these guys are going to cancel out. And so, and then note that this is the volume 1 and 3 are along an isochoric line. So this really is 1 minus pressure 1, pressure 3. So then if I start putting this in together, I'm going to get 1 minus, looks like it's 4,000 kilopascals, 100 kilopascals, which then tells me that this is going to be 75% for the Carnot efficiency. So I now know what this value is right here. Okay. So what does this tell us right here? What this tells us here is that I have a maximum efficiency, right? The maximum efficiency of this engine is 75% efficiency, right? And this is a whoppingly large efficiency, right? That is a huge efficiency. So now let's go to the next thing. So now we're going to look at for the engine efficiency. And this guy is eta of the engine. So what we're looking at here is that we have this. So for a real engine, and what do I mean by a real engine? That means that it's not a reversible path. So for a real engine, I know that the engine efficiency is what? It's really 1 minus the cold, hot, which is the same as 1 minus the heating of Q31 to Q23, where these heatings, because when you look at them, note that we have constant volume heating for Q31. So that means, because this is a diatomic gas, it's going to be Nr delta T31. And then I have constant pressure heating. And this guy's Q23, but this should be 7/2 nRT, nR delta T between 2 and 3. So we have to compute that. So let's go look at that. Now, the one thing that we see here is that we do not know any of the temperatures. Which means we must calculate, in order to answer this question, T1, T2, T3. On the other hand, we know P1, P2 equals to P3, and V2. We do not know V1, V3 equals to that. So what we can do here is that if I calculate the temperatures, I got to calculate 3 quantities. This, I own here, we only have one unknown. So it makes sense not to calculate the temperatures. So here we go. So that means here is that our goal is to calculate V1, V3. And then once we have that, we have everything that we need here. So the one thing that we got to pay attention is that you got to keep looking at the cycle. Okay, so let's say that this is my cycle right here. I want to make it a little bit smaller. So when I look at my cycle right here, I need a quantity that's going to include volume. I know that if I look along path 1 to 2, that tells me that I have P1 V1 gamma, and then this will give me P2 V2 gamma. So that has right here. So this, excuse me, this contains V1. So this is what we're going to try to solve for. Now, the other way that we can look at is that you can look at the path between 3 and 1, but when you look at that path, that's isochoric, and isochoric tells you that it's really what? It's the pressure at 3 times the temperature at 3, the pressure at 1 times the temperature at 1. So this doesn't include the volume. So this tells us that we can't go along that path. We have to solve the adiabatic curve. So here we go. I'm going to use the adiabatic condition to solve for V1. So I see that P1 V1 gamma is equal to P2 V2 gamma, isolating, right? So now I got to isolate V1. So that means then, so if I move over P1 to the other side, I'm going to have P2, P1. But note what I got to do. I got to take the inverse of gamma. So if I take the inverse of gamma, then if I take the inverse of gamma for V2, I just get V2 here. So now if I just pick off the values from the table, here's what I see. I see that this is going to be 400K, 100K, and this will be to the 5/7 power. And then I have 10 to the minus 3 meters cubed, which then gives me 2.69 times 10 to the minus 3 meters cubed. And this is V1, V3. So now I have all my quantities. I have all the pressures, and I have all the volumes. So now I can calculate all the heatings. So here we go. So now we want to calculate the 2 heatings and the work done. So here I go. So the first one's going to be the heating Q cold. So if I look at the heating Q cold, here's what I see. So remember, I need to take the absolute value of Q cold. It has to be a positive quantity because the efficiency already has the minus sign in there. So here I go. So then it's got to be the absolute value of 3,1. So in this case, it's got to look like this. It's going to be 5/2 NR delta 3,1. And then I use the ideal gas law, and this is going to be 5/2, and this is going to give me P1 V1 minus P3 V3, but the volume is the same, so I could pull out the volume, so this will be 5/2, the difference of P1 P3 times the volume 1. Now, when I punch in numbers here, this is a negative quantity. So remember, I need the absolute value. So this is going to be 5/2, and then look what I'm going to get. I'm going to get 100 minus 400, and this will be times 10 to the 3. You could see there's my negative number right there. And then my volume is 2.69 times 10 to the minus 3. And look what happens to those minus 3s there. See that? That's positive That's negative, so it goes to 1. And this will be in units of joules. So if I compute this, remember, this is a negative number, but if I take the absolute value of this, then I'm going to get a value that reads 20.2 times 10 to the 2 joules, but I'm going to write this as 2.02 kilojoules, and this will be Q31, which is the same as Q cold. So I now have my first heating. So now let's go get the next one. So the next one is then going to be heating Q hot. So if I look at this, I then see that Q hot, this is automatically a positive number already, is Q23, and this is at constant pressure. So then I'm going to use the same type of thing. If it's constant pressure, I can pull the pressure out. So that then this is 7/2. So then it's got to be P3, V3, P2, V2, but the pressures are the same. So then this is 7/2, P2, V3, V2. So now I'm just going to punch in my numbers, and my numbers is then going to be 7/2. And look what I'm going to get. I'm going to get 400 times 2.69 minus 1, and then I'm going to have 10 to the 3 times 10 to the minus 3, and again, this quantity cancels out, and so this will be in units of joules, so then I'm going to get a value that reads 3.77 kilojoules, and this will be the heat from 2, 3, which we've identified as Q hot. So then the last thing that I need is that I need to look at the mechanical work. W out. And this comes from the first law. So from the first law, the work out is equal to Q hot minus Q cold. So then you could see here that this is going to be what? 3.77 minus 2.02, and of course, kilojoules. And this is then going to give me, remember, kilojoules. And so this will give me 1.75 kilojoules for the output work. So now I could then go in and calculate the efficiency. So now the heat engine efficiency is, remember, I can write it a couple of ways. The easiest way is just out divided by Q hot. I could have used 1 minus Q cold divided by Q hot, but if I do this here, this is going to be 1.75 kilojoules divided by 3.77. And if I compute this, I get 0.464, which then tells me that this is 46.4% efficiency for the engine. So now I have this quantity right here. So now what I'm going to do here is that if I look at my efficiency, the Carnot efficiency, so if I comparing the maximum efficiency of Carnot versus that of the engine, we see that eta of the Carnot, which in our case was 75%, is greater than the engine efficiency, which is 46.4%. So what all this does here is it says this heat engine does not violate the second law of thermodynamics. So then the last thing that we should be looking at is that I want to look at what does my system look like then. So if I look at my heat engine, my energy transfer diagram, so the energy transfer diagram, it reads something like this. So I have a hot reservoir. I'm going to go, see, let's go from here. Maybe that's a little bit too much. How about if I go from here? Let's look at something like this. So I'm looking at 1, 2, 3, 4. So if I look at this thing here, then this is going to go down to the cold reservoir. Now, the heat engine is about 50%. So I'm going to say that this is about this much. So this amount goes into the cold reservoir. So in other words, this is what I'm saying. Here's my hot reservoir. And when you're looking at this, you could see here that this guy is about 2 squares thick. So half of the energy goes into work and half of it goes into the cold reservoir. So if I'm looking at my heat and my output work, it's looking something like this. That's about half. And then over here, here's my cold reservoir. And you're seeing that this is about half too. So that means over here, I have T hot. Here I have T cold, which we did not calculate. And then what you're seeing here is that here, you're seeing that I have a big, thick arrow. And it's this arrow that's Q hot, which is 3.77 kilojoules. Part of it goes to the output work, the mechanical work, which is 1.75 kilojoules. And then part of it is going to Q cold. And this number is 2.02 kilojoules.